Okay, let's practice matching some correlation coefficients with their scatter plot. So I'm going to start with the extremes with r equals 1. That is a perfect positive linear trend. So what I see is that matches the very first graph. That first graph is perfectly linear. A line goes exactly through all of those points and it's positive. So this will be my r equals 1 option. And now r equals a negative 1 needs to be just as perfect except in the downward direction. And that would be the very last graph. Very strong, perfectly strong actually in the negative direction. Now I'm going to sort of work my way in. So on an r equals 0.98 is a very, very, very strong positive linear trend. So kind of looking around at what my other options are, I think that's going to be the men life expectancy versus women life expectancy. It's still in a positive direction. Those points are very clustered together, giving it an almost perfect trend. So 0.98, almost perfect. But not quite, right? There are a few points that scatter a little bit, so it brings it down just a bit. Now my next one is 0.72. So we're starting to get a bit more scatter at that point, but still clearly in an upward direction. That's going to be this height versus weight. A 0.72 trend on that one. So a lot more scatter is starting to happen here. It's not as strong. My value's starting to kind of drop here, but still definitely very positive. I'm starting to get some deviations, though, from this main positive line. Now, my next option is 0.48. At this point, still positive, but we would be experiencing a lot of scatter and a lot of deviations. So looking around, I think I'm going to have to go with the city government income versus private income. It is still trending upward. These points are still going in general up from left to right, but we have a lot of scatter. A lot of those points deviate quite far from that line. I'm going to sort of come down from the other side now. A negative 0.79 R value would be pretty strong, but in the negative direction. So I've got a couple that still look like they're in the negative direction, and definitely one is stronger than the other one. This literacy rate versus total bursts per women that we looked at before, well, now we can actually qualify that. We said we thought it was somewhat strong when we first looked at it, and now we actually have a value for it. It's got an R value of negative 0.79. Negative means downward, and 0.79 tells us exactly how strong. So not super strong, but, you know, definitely somewhat strong, definitely closer to -1 than it is to 0. My R value of negative 0.35, that's getting to be pretty close to 0. That means there's going to be a lot of scatter. Maybe I can barely even tell that it's in the negative direction at this point. This is going to be the total football carries versus yards gained per carry. It is still moving downward, kinda, sorta, a little bit, but we have lots of points that are deviating from where the bulk of that data seems to be. So a negative 0.35 would go there. And then an R value of 0 means there is I cannot put a positive or negative direction to it. It sort of just looks like someone threw points all over the page and there's no trend whatsoever. That looks like age in years versus time in hours, and I do believe that this is actually time of finishing a marathon. So it does not appear that age and the time it takes to finish a marathon actually are correlated whatsoever. Probably what makes more of a difference there is your overall physical health and your training, and someone who is much older than me could probably run that a lot faster than me because I don't train and that is not something that I do. So it doesn't appear that those two things are correlated at all. There's another value that's important with these correlations, which is called the coefficient of determination. And that is the correlation coefficient squared, so R squared. You usually multiply this value by 100% to convert it to a percentage. So whereas we give R values as decimals, usually we give our final R squared value as a percent. Since your R value is somewhere between -1 and 1, when you square numbers between -1 and 1, you will end up with an R value either between 0 and 1 or between 0% and 100%. A value of 100% means that the relationship is perfectly linear and the regression equation perfectly predicts your observations. A value of 0% means there is no linear relationship and the line would do a very, very poor job at predicting observations. So it's kind of like how good is our line? How good is that linear regression? That's what this value tells us. So what we say is that R squared percentage of the variation in Y is explained by the X value. So how much, like what percentage of that Y value is actually explained by the X value. So let's go ahead and create this best fit linear regression equation for our flight times from Boston data. And we're going to give it rounded to 2 decimal places. So I've brought that data back up, but I've cleared off the actual scatter plot that we had made. And let's make it again. For some reason, the option, for me anyway, to create this regression equation, it disappears unless I'm doing it right after I've created the scatter plot. So I'm going to re-highlight my input and output values. I'm going to go back to Insert and just remake this scatter plot. So we've already done that. When you have just created one, you should have an option to add chart elements. And for me, like I said, and again, I'm using kind of the 365 web version of this, so this may not happen to you, but it does to me. This disappears after I've like left this kind of option. But I should be able to add all kinds of elements. I can add titles and make labels and I can add all kinds of things, but what we want to add is a trend line. And we want to add specifically a linear trend line. So it's added that there. I can click on that trend line. Oops, okay, so at that point, linear. Okay, so I should be able to go to more options at this point. It's not giving me more options. Or I want to format my trend line. So I can do all kinds of things with it. I would like to, and this is noted here, you can choose to display your R squared value. I want to display that, and I also want to display the equation for this because I've got the line showing, I can visually see it, but I don't know what the equation is for it yet. So I want to display the equation on the chart. So again, I just kind of clicked on the line and this option, the format option, came up. I want to format it. So on these directions say more options. I had to actually click format trend line in order to get that to show up. So I'm just going to go ahead and you can make your trend line different. You can make it solid. You can make it different dashes, different colors, things like that. If you want to make it really stand out, maybe you want to make it red. Okay, but anyway, what's most important for us right now is that we have this equation. So I'm going to round that off to 2 decimal places each for my recording. So in my recording here, I'm going to write this as y equals 1.84x plus 0.84. Just so happened that those 2 values say both 0.84. That's a coincidence. And the R squared value is, as we can see here, the 0.9894. So the R squared value is 0.9894. We usually give this as a percentage. So I'm going to call this 98.94%. And what that means is that approximately 98.94% of the variation in flight times, that's the Y, is explained by your distance that you're traveling. The rest of the variation of a flight time is due to something other than the distance you're traveling. So then that piques my interest as to what else might influence a flight time, completely irrelevant to how far you're going. So that could be stuff like maybe the weather, right? The weather could cause faster or shorter flight times and have nothing to do with how far you're actually going. Or the wind, whether it is going with you or against you. Maybe there were loading problems, right? That could cause longer flight times, etc. So there are other things that can be attributed to a longer flight time, but most of it, 98.94%, really is based on how far you're traveling. Interpret the slope in context. Okay, so on this one, it would be that as the x value, so as your distance traveled increases by, and it's 1, but in this case it's 1,000 miles specifically, so 1, we're counting in thousands, so increases by 1,000 miles. The flight time tends or will, or we expect it to, I guess. Let me say that better. The flight time is expected to increase by about slope, so 1.84 hours. The y-intercept, and does it have a practical meaning? Because sometimes it doesn't. In this case, our y-intercept is 0, 0.84. Again, remember that 0 is the distance and the y value is the flight time. So does this have any meaning? What it's telling us is at 0 hours of distance traveled, we expect a flight to take about 0.84 hours. This one's a little bit on the borderline here. I think this does still have meaning because you haven't moved yet, but maybe this is that loading time. Announcements, etc., that you hardly ever take off exactly on that time where they're saying you're going to take off because you've got this other stuff going on. Seattle being about 3,000 miles from Boston, how long should it take to fly nonstop from Boston to Seattle? Okay, so let's sub that in. We've got y equals 1.84 times, we put this in as just a 3 because we're counting in thousands, plus 0.84. And you can calculate that out, and that comes out to about 6.36 hours. That's how long we would estimate that flight to be. Again, this is an estimation. And then Sydney, Australia is 10,085 miles from Boston. Estimate how long it should take to fly nonstop from Boston to Sydney, and should we trust this estimation? If we put that in here, it would be 10.085. And again, you can do that on your own. It comes out to about 19.40 hours. Should we estimate, or should we trust this estimation? My answer to that is probably not. Based on the data that we've got here, the farthest distance that we even have recorded to go by is so the largest distance we have is just over 3,000 miles. And here we're trying to estimate a distance of over 10,000 miles. So this is probably not going to be very trustworthy.